Okay, let's now show that this forms a group. Okay, so let's start going through our axioms. So first off, we can say that it's closed since there are no new elements in the table. Okay, number two, associativity. So you're allowed to assume that the composition of transformations is associative. So I can just say associative since the composition of transformations is associative. Okay, number three, we have to see if there's a unique identity in the set. And yes, there is. The unique identity in the set is E. And finally, number four is our inverses. So we're going to have to write out all the inverses of the elements. So the inverse of E is E. The inverse of R1 is going to be R2. And if we just look, the inverse of R2 is going to be R1. And remember, inverses, they come in pairs. So if one is the inverse of one, and the other is the inverse of the other. Okay, so I can fill that out a bit quicker. Then let's do S1. Okay, so the inverse of S1 is itself. So what you'll notice is that all the reflections are self-inverse. So S2 inverse is going to be S2, and the S3 inverse is going to be S3, like that. Okay, so then I can conclude, therefore, each element has a unique inverse in the set. And then I can say, therefore, since all four group axioms are satisfied, it's a group. Okay, so that's the proof complete there. Now the next part says find the order of the elements and determine if the group is cyclic. Okay, so order of the elements then. So the order of E is going to be 1. Okay, because the identity order is always 1. Then the next easy bits to do are the reflections, because they're all self-inverse and they're not the identity. We know the orders are going to be 2. And then let's do our rotations. So R1. I mean, you can use the Cayley table to do this, but also logically, if you rotate by 120, rotate by 120 again, then rotate by 120 again, you've rotated 360, which is the identity. So the order of the elements should be 3 for R1. And then for R2, okay, given that that's the inverse of R1, we know it's also going to be 3. And remember, the order of an element is a factor of the order of the group. So the order of the group is 6. Okay, so all my element orders make sense. Now we have to determine if it is cyclic. Well, if it's cyclic, there'll be an element with the same order as the group order. Okay, however, there is no element of order 6. So therefore, this group is not cyclic. Okay, so therefore, group is not cyclic since no element with the same order as the group. Okay, now we have to check if it's abelian. Now this would have been easy if it was cyclic, because all cyclic groups are abelian. However, it's not. However, some non-cyclic groups are still abelian. So let's just go and investigate our table. Let's look at our leading diagonal. Okay, are we symmetric about our leading diagonal? Okay, and what you'll notice is no, we are not. So for example, if you take this entry here and this entry here, they should be the same. okay, if there was symmetry, but there is not. Okay, so we found ourselves a counter example. Okay, so the one that comes out as S3, that is S1, combined with R1, that comes out as S3. Okay, whereas when we do R1 combined with S1, that comes out as S2. Okay, so therefore we found our counter example, therefore not abelian. Okay, so your group of symmetries is a non-abelian, non-cyclic group. Now, in terms of sort of a name that we can give to our symmetry group, these are called dihedral groups. And the notation we use to represent them, which you don't technically need to know, is either dn or d2n. So n represents the number of vertices on the shape. So we could call this one d3, or we could call it d6, which is a bit confusing, okay, because there are essentially two conventions for this. I think the one that's more commonly used is this one here, but you don't have to worry about this notation, as I don't think it will actually come up in the exam. But a dihedral group is just a set of symmetries, including rotations and reflections, of a regular n-sided shape. Now, just one little follow-up question. Give an example of a group of order 10. Okay, well, thinking about what I've just said, then if we look at our equilateral one, which is D3, well, the order of this one, so the order of D3, using this convention for the notation, is equal to 6. Okay, so times by 2. So if we want the order to be 10, well, then you'd have to consider D5, okay, which is the group of symmetries of a regular pentagon under the composition of transformations. Okay, so if you ever asked to give an example of a group, this is quite a convenient one, especially if they ask for a non-cyclic, non-abelian one, okay, because that fits this scenario.